good morning or good afternoon or good evening. Uh, th- this particular course is a follow-up of what you learned in solid state devices, and we'll be using concepts you learned in electric circuits. And a quick recap of what you did in solid state devices. One of the first devices you would have learnt about in solid state devices is a p-n junction diode. As you remember, a p-n junction diode is a semiconductor diode made of a p-type semiconductor material and an n-type semiconductor material, and it has two terminals, the two terminals being anode and cathode. And the diode is said to conduct when it is forward biased. The diode is forward biased when the anode of the diode is connected to the positive end of the supply and the cathode is connected to the negative end of the supply. And if you reverse the connection, connecting the positive end to the cathode and the negative end to the anode, the diode does not conduct. Therefore, this particular characteristic of the diode means that it can be used for the following applications. You can see it can be used as a switch, a rectifier, clipper, clamper, and so many more applications, about which you will learn in the following units and semesters. And an ideal diode should have characteristics of a switch, which means when it is forward biased, it should conduct. That means even for 0 voltage, current should increase or current should flow without any restriction. And when it is reverse biased, it should act like a open switch and current should not flow even when a very high voltage is applied. But then this is the ideal case. So if it were an ideal case, then you could perfectly use it as a switch. But then actual diode or diode in real life does not have ideal characteristics. So the characteristic of a diode, before we look at the characteristics of a diode, we look at the characteristic of a DC source. A DC source gives out constant output voltage for any load current. So that's why you find a perfectly vertical straight line. And then this is a characteristic of a resistance. And if you remember Ohm's law, R, the resistance, is equal to reciprocal of the slope of this characteristic. So it will be V by I. Delta V divided by delta I will be the slope of the characteristic, will be the reciprocal of the slope of the characteristic. Slope would be delta I divided by delta V. So R is equal to delta V divided by delta I. So that is a characteristic of a resistance. Take a look at the characteristic of a diode. Now, if you remember, although we say the diode conducts when it is forward biased and does not conduct when it is reverse biased, you look at the characteristic, it does not start conducting straight away when it is forward biased. If it were a silicon diode, the diode actually starts conducting only after about 0.7 ohms. That is the potential across the depletion region. So unless the applied potential exceeds this potential, this is for a silicon diode 0.7 volts and for a germanium diode it is 0.3 volts. So unless it exceeds this voltage, it does not conduct. So you see, till about 0.7 volts or 0.3 volts the diode does not conduct, and after that you find the diode starts conducting. So the voltage starts in current starts increasing steeply for very little increase in voltage, and on the reverse side you find no current, hardly any current flows on the reverse side. That means when the diode is reverse biased, it really does not conduct. So this characteristics of the diode means we can draw an equivalent circuit of a diode. Equivalent circuit of any device is a circuit drawn using only the passive components and the power supply. So here we have the equivalent circuit of the diode. So this represents the diode drop for the 0.3 volts or 0.7 volts for germanium or silicon diode, and to represent that voltage we have a voltage source, and then to represent the slight slope in the characteristic, if it had been a perfectly vertical straight line after it turns on, then we wouldn't have this resistance, but then it is not, and therefore we include a resistance to represent the diode resistance or the slope in the characteristic. So this is an equivalent circuit of a diode. The first commonest application of a PN junction diode is a rectifier. So the rectifier is, although people simply say rectifier converts AC to DC, it does not conduct AC to perfect DC. It is the first stage of converting AC into DC, because what a rectifier does is it converts, now AC itself is a sinusoidal voltage, that means every half cycle the voltage changes direction. So for half cycle it is positive, for the next half cycle it is negative. So what a rectifier does is it converts this bidirectional AC voltage into a unidirectional voltage. So either, depending on how you connect your diode, you have only one half cycle. That means the diode conducts only during the positive half cycle. So depending on the type of rectifier, you either have the diode conducting for one half cycle and not conducting for the other half cycle, in which case we call it a half wave rectifier. So you do not have an output for half cycle. Or if the diode conducts for both cycles, you call it a full wave rectifier. Now you have two types of full wave rectifier: center tapped rectifier and bridge rectifier. So a center tapped rectifier uses two diodes instead of one, and a full wave bridge rectifier uses four diodes. So half wave rectifier uses simply one diode, full wave rectifier with center tapped transformer uses two diodes, and a full wave bridge rectifier uses four diodes. Now let's start with a half wave rectifier. Now I said this is the first step of converting AC voltage to DC. So if you look at your applications in your daily life, you find you have adapters, you have phone chargers that requires DC voltage, and the magnitude of the DC voltage required is small. It is 9 volts or 12 volts or simply 6 volts. So depending on what voltage you need, the first step, that's why you have a transformer that steps down your AC voltage to the required value. Suppose you need a 12 volts DC supply. So here you have a transformer that converts 230 volts supply that is available in all homes. So that's the domestic supply available. So converts 230 volts to 12 volts. So now your total voltage is from plus 12 to minus 12. So across you have totally 24 volts. So now you have, or you could have from plus 6 to minus 6 also, in which case it will be plus Vm to minus Vm will be 12 volts. So here you have, that's your input voltage, let's say 6 volts to minus 6 volts. So that's your sinusoidal input voltage to the rectifier, which is available at the output of the transformer, and one end of the transformer is connected to a diode, and the following the diode you have a load resistor which also acts as a limiting resistor, because once the diode turns on, current flowing through the diode can increase enormously. So if you do not limit the current, it can burn the device down. So therefore it is essential to limit the current flowing through the diode, and therefore you always have to use a resistor in series with the diode to limit the current flowing through the diode. So there you have your load resistor that acts also as your limiting resistor, and the output voltage is taken across the load resistor. So now the second waveform below the input waveform is the output waveform. So what happens is, I said diode conducts only when it is forward biased. That means only when the applied voltage to the anode is positive will the diode conduct. So there you have, during the positive half cycle the diode conducts, negative half cycle it does not conduct. So one half cycle you have sinusoidal waveform, and when the sinusoidal waveform of the input waveform goes negative, the output becomes 0. So you only have half of the sinusoidal waveform available at the output. And now just like so, that's your output waveform. So what you have is, you have eliminated the negative part of the waveform. So you don't have reversal of direction, you only have increase and decrease. So now just like any device that you buy, if you buy a motor, you look at the horsepower of the motor, you look at the efficiency of the motor, or if you go buy a computer, you look at the screen size, resolution, you look at the RAM capacity and so on. Similarly, when you look at a rectifier, there are two parameters that are of importance. One is ripple factor, the other one is efficiency. So in order to, what is ripple factor? Efficiency, of course, now we are using a diode as a first step of a to convert AC voltage to DC voltage. So efficiency would be ratio of the DC power available at the output to the AC power available at the output. So that would be efficiency. And what would be ripple factor? The definition of ripple factor is, it is the ratio of the RMS value of the AC component to the DC component in the output. So it is, if I give you the equation, it is RMS value of AC component to DC value of the component. So that's the definition for ripple factor. In the next class, in the next video, we'll derive an expression for ripple factor and efficiency.